Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 32. We're going to discuss the chi-square distribution in this video. So last time we finished up the gamma distribution. We talked about the mean, the variance. We talked about the relationship to the exponential distribution. So this is important to know these relationships. So a gamma 1 theta is a exponential theta. Today we're going to talk about, in this video, the chi-square distribution, which is another gamma distribution. So let's get started. We say that a random variable x has a chi-square. This is chi-square distribution. And so this is the Greek letter chi. It's not chi, it's chi. Okay? So we can say that x is distributed as a chi-squared distribution with r degrees of freedom. And we will talk about degrees of freedom later, but now we're just going to accept that we have degrees of freedom. Okay? And that's r. So if x has a gamma distribution with theta equals 2 and alpha equals r over 2, and r is a positive integer. So there's a couple of ways to write r. I could write it as the natural numbers, and I could write it as integers positive. So those are a couple of ways that you can write it in set theory. So just thought I'd mention that in case you're interested, or in case you see that somewhere else if you go to grad school. All right, so substituting in alpha equals alpha equals r over 2, there we go, and theta equals 2, we end up with this distribution here. And so r is, again, we can write it as r in the natural numbers. So it's a positive integer. The mean, I'm going to use the mean for the gamma, and I substitute, which is, because this is a gamma distribution, I just substitute in alpha theta. So alpha is r over 2, theta is 2, so the mean of the chi-square distribution is r. Nicely, very nicely, sigma squared, the variance, is alpha theta squared, r over 2, 2 squared, 2r. It's not very hard at all. Now, I just have to substitute in for theta and for alpha in the moment generating function, and easily enough I come up with this as my moment generating function. Let's take a look at what the chi-squared distribution looks like. And I tried to reproduce this from the book. So when r is equal to 2, then you have what looks like an exponential distribution, right? When r is equal to 3, it looks like a gamma distribution. It's a skewed distribution, but you notice that the peaks aren't quite as high as some of the, for theta, because theta is equal to 2. This is a gamma distribution. Remember, so that theta is equal to 2. So if you look back at the gamma distribution, theta equals 2, you'll see this. But what happens when we change alpha, which is in the gamma, or we increase it, and r is what controls that here, because alpha is r over 2. The 2 stays the same on the bottom, and so as we, so this is alpha equals 3 halves, or 1.5. Here's alpha equals 2.5, and here's alpha equals 4. So that's this, even though it's not drawn very well, that's this line here. Okay. So that's what happens as r increases. This gets more spread out, and there's more variation. So because again we're changing we're changing the shape, but it gets more variation. So this is such an important distribution that there are tables for the CDF, and in fact that's in table 4 in Appendix B. And so we're going to use that. I do recall that I forgot to pull up the table for this video, so I will do that now. If I have the, I do not, yes, I do have the chi-squared distribution, great. And so we'll go back here and let's look at our example. So, oops. So sometimes that happens with my iPad, it just freezes. So in this example, I'm just going to say that x is chi-squared 5. And we want to find the probability, oops, that x is between 1.145 and 12.83. Remember that this is always going to be the CDF of f, or so capital F of the largest number, minus the CDF of the smaller number. And so I need to go to the table and look up for chi-squared 5 degrees of freedom, I need to look up and find 12.83. So let's look at this table and see how we read it. So chi-squared 8 is given here, and of course here as well. And so we have the shaded region here, and so this is the CDF, the shaded region, right, up to x. Here's x. And they give you the formula for the CDF, which is very nice of them. And then we have, for the critical value, this is called a critical value, chi-squared alpha of 8 is what our distribution is. So alpha, when we see this subscript, that is the probability to the right of this number. So that's why you see alpha up here, okay? So that is the form. Please take time to get used to that and familiar with it. So let's see what we can do here. We have 5 degrees of freedom, so I'm going to line up the bottom of my iPad screen with 5. And I'm looking for two numbers. I've forgotten what they are. The first is 12.83, so let's go look and see if I find, and lo and behold, here is 12.83. Now, I can either look at this or this. In this case, in my problem, I want the CDF. So I want capital F here. So that means I'm going to look at the CDF portion. And the CDF, as you see, is the shaded region here. And so this says probability, a little confusing, but this says probability that x is less than or equal to x. I think I would have made this a dotted line or something, so that you know that that goes with this p of x less than or equal to x. And so this is the value for the CDF, so 0.975. And so we write down 0.975. And then we go look in the same row, 1.145, and I find 1.145 here, and the CDF that goes with that is 0.05. Oops. And so we go back and we put 0.05. And when I subtract that, I get 0.925, which is my answer. So let's look at another one. Let's find the probability that x is greater than 15.09. Again, we still have we're in the same distribution, 5 degrees of freedom. So we're looking for 15.09, but now we want greater than. And so we come over here, and I'll clean up a little bit so we can find what we're looking for without distraction. And I want, I want what value again? It was 15.09. All right. So I find 15.09, but I want greater than. So now I look here, and I see that the alpha is, so alpha equals 0.01, and alpha equals the probability that x is greater than this value, chi-squared 0.015. Okay. And that, so alpha is equal to that, so this is equal to 0.01 in this case. So 0.01 is going to be our answer. So I could get that directly here. Or I could use, so this I could just put 0.01, or I could use the CDF. And if I look back, the CDF here was 0.990, and I can do 1 minus that. Oops. So 1 minus 0.990, which of course gives me the same answer. So so we don't really have to do this step for this table. They have given us the greater than as well as the CDF or less than. So let's do an example. Excuse me. So let's say that X has a chi-squared distribution with 7 degrees of freedom. We want to find the two constants such that A and B, such that the probability that X is between A and B is equal to 0.95. We are going to be restricted by the table. So it's always handy to draw a picture and see what you can find. So we need 0.95 to be between them. So we look at the chi-squared table. I'm going to zoom out a little bit so we can see the whole top line here and clean this up. And I'm looking at the CDF because this is an easy way to do it. You could look at the alpha values if you want to, but I find it easier to look at the bigger numbers, probably because I'm older. And so if I look at 0.990, is there any way I can subtract one of these numbers to get 0.95? And the answer is no. So then I can go to 0.975. Now I don't want 0.95 because there is no 0 here, right? There's no 0, so there's no way for me to subtract the 0. So I want two numbers, and it doesn't, and so I don't want 0 as one of them. So that means I need 0.975, and what can I subtract from it to get 0.95, and that's 0.025. And so this was 7 degrees of freedom, and so my smaller number is 1.690. My larger number is 16.01. And those are my answers. Okay. Now, I told you I've already gone over the critical value. If you need to look at that, please do. We could also say that this is the percentile. The critical value is also the percentile, the 101 minus alpha percentile. Or you could call it the 100th alpha, I left off alpha, upper percentile. Okay? And this with the R degrees of freedom. So let's do one last example, and this is a very important one. If customers arrive at the shop on the average of 30 per hour in accordance with, IAW is in accordance with, by the way, that's not jaw, that's I. It's supposed to be a little I. IAW in accordance with a Poisson process. What is the probability that the shopkeeper will have to wait longer than 9.390 minutes for the first 9 customers to arrive? Okay, so in accordance with 30 per hour. Now, we're changing this to minutes. This is hour, this is minutes. So let's look and see what lambda is. Lambda is going to change from 30 per hour to 1/2 per hour, which makes theta equal to 2. And right about now, alarm bells are going off, and I say, well, if theta is equal to 2, I can use a chi-squared distribution. Remember that alpha is equal to R over 2. So alpha is equal to R over 2, which is equal to, what did it say? 9. So I need to solve for R. R is 18. So I have a chi-squared with 18 degrees of freedom. And it asks me, what's the probability that the shopkeeper will have to wait longer than 9.390? So that's what I want. And again, I don't even have to do this step. I can just do that directly, or you can use that step. That's up to you. So I'm going to just go directly to here by going to the table and looking for 9.390. And I have 18 degrees of freedom. And so I want to look for 9.390. Here it is. And that tells me that the probability that it's greater than that number is 0.95. Or I could take 1 minus 0.05, right? They both get you the same value. So, but I can look it up directly, 0.95 using this table. And, oops, and that is exactly what we have here. So now, let's, another example, let x be exponential 2. Notice that, remember that exponential 2, this is a gamma 1, and theta equals 2. So exponential has an alpha of 1. So we know that this is the PDF of the exponential, but now let's go to the gamma distribution function and plug it in, and let's make this, since this has theta equals 2, it's also a chi-square. What? So since since alpha is 1, then alpha equals r over 2 equals 1. R is equal to 2. So we could substitute in r over 2, that's 2 over 2, 2 over 2, 2 over 2, x, and the 2 theta. So theta is equal to 2. So the chi-squared, this is also a chi-squared 2 distribution, okay? So it's exponential 2, is a gamma 1, 2, is a chi-squared 2, okay? So that is something to note. So that means that we can, if we have an exponential, as long as it's an exponential 2, we can use the chi-squared distribution. So I want to find the probability that x is between 0.051 and 7.378. Remember that r is equal to 2, so we're looking at 2 degrees of freedom. 051, 738. See if I can remember those. So 2 degrees of freedom, we're here. 0.051 is here. And 7.378 is here. And if I look at that, I can use, I want to know it's between, so for me, it's easier to use the CDF, but if you want to use, you'll get the same thing, because here is 0.975, here's 0.025, they reversed because of symmetry. And so it's going to be 0.975 minus 0.025, which is 0.95. So that's it for the chi-squared distribution. There are no other videos for this. I just did it in a slightly longer one for continuity. So please don't forget to scan and upload your lecture notes before midnight, the date listed on the course calendar. You'll want to definitely update your list of distributions with the chi-squared distribution. Please make notes of the relationships between the chi-square, the exponential, and the gamma distribution. If you have questions, by all means, come to my virtual office hours. If you can't do that, then email me a picture of your problem and a picture of your work so I can help you by email. Take care of yourself. Until next time.